Almost all the acid and base catalyzed nucleophilic addition reactions we've looked at so far are ones where the nucleophilic atom is the heteroatom, like a nitrogen or oxygen or sulfur. Now, reactions that involve carbon nucleophiles are super important to organic chemistry. And these include aldol reactions. And we're going to look at aldol reactions through the rest of the chapter. Um, so you may be asking yourself, what is an aldol? An aldol is it's just a molecule that contains both a carbonyl group, which we have here, which is the kind of the aldehyde, right? That's where the ald comes from, and an OH group, like an alcohol. It's attached to the beta carbon, and that's where the OL comes from, of the alcohol. And so what we see here is when we talk about the beta carbon with carbonyls, with aldehydes, in this particular instance, the alpha carbon starts at the carbon next to it, and then the beta carbon follows that. Um, and so in this particular reaction that we're looking at, ethanol is treated with sodium hydroxide, and then the product is, of course, 3-hydroxybutanol. And what we notice here is that a new carbon-carbon bond is formed, right? And so this is super important in chemistry. And I also want you to notice that the carbonyl and the hydroxyl groups in the product are separated by those two carbon atoms. That means this is also classified as a beta hydroxy carbonyl compound. So we can call it an aldol, or we can call it a beta hydroxy carbonyl compound. And this is just the general form, of course, of any aldol addition product. And every aldol addition product is going to produce that beta hydroxycarbonyl compound. The particular one that we see here, that 3-hydroxybutanol, is a component of cigarette smoke. It's also hypotonic, so it was once used in medicine as a sedative, which I think is just kind of interesting. So, an interesting example here. You know what else is interesting? The mechanism. So let's look at the mechanism of this aldol reaction. All right, so let's start by drawing our reactants here. So we have our friendly aldehyde, okay? And we are going to add that base, and so we've got the OH minus right here. Okay, and so what the OH minus is going to do is it's going to deprotonate the alpha carbon. And so when it deprotonates the alpha carbon, it's going to come in, it's going to grab that proton. Those electrons are going to go on the carbon here. And what you're going to get is an enolate ion. Okay, and so what we have here, the oxygen here. Okay, and so, and those are electrons. I don't know why it's not showing up really great, but there we go. Those are our electrons. All right. And so what you may notice here, right, is that maybe this, doesn't look like it would be super stable. But the kind of nice thing is that it is resonance stabilized. And so we do have a resonance structure here that looks like that, okay? Now, this, even though it's resonance stabilized, it's important to note that this proton transfer reaction still heavily really favors the reactant side. So at equilibrium, only about 0.01% of the aldehyde is deprotonated. Okay. Now, so we've got this enolate ion, and then what we're going to see here is that it's going to attack, the nucleophile at the carbon is going to attack a second molecule of that same aldehyde. So remember, we've got lots of molecules running around in our flask, and this means we're going to have more than one molecule of the aldehyde. And so what's going to happen are these electrons are going to come and attack here, right? And then these electrons are going to come up and attack here. And so I forgot to write down that this right here is a proton transfer. And this second reaction here, right, is a nucleophilic addition. Okay, and so now what we have is this guy. And then what we're going to see here is another proton transfer involving water. Right? And now we have that molecule. The other thing I want you to notice is that the base here is regenerated. Right? So that means that's a catalyst. So that's why we have a base catalyzed reaction here. The nucleophilic addition step here is reversible. So overall, this reaction is also a reversible reaction. So I want us to do an example. So if it cut up there, I just had to pause it really quick. All right. So let's look at this molecule here. It says, show how to synthesize the molecule shown here using an aldol reaction. And so when you have to think backwards, right, for that retrosynthetic analysis, which is really what we're doing here, we need to think back, how can we undo this? And so can you identify the portion of the molecule that characterizes it as a beta hydroxyaldehyde? And so when we look at this, we need to say, okay, hey, look, I know that the aldehyde has an OH group, and I know it's got the aldehyde group there. That's part of the aldol, right? And the alpha and beta carbons of the carbonyl group, right, are right here. So here's the alpha, and here's the beta, right? Boop, right like that, right? And so an OH group is going to be attached to the beta carbon, right? So we know that this is that beta hydroxy aldehyde. And then if we're going to undo an aldol addition, we need to kind of cut it right there. Okay. So to undo this reaction, as I mentioned, we're going to disconnect these two pieces here, right? And so we disconnect these two pieces here, and we are thinking backwards, right? We would have to start with this guy out here, right? Down, up, down, like that. And we would need two of those, okay? And so what I'm looking at here when I do this is I'm saying, okay, hey, look, this is a piece here all the way through here to this. And then I know the second piece that comes in, I'll try to do a purple highlighter here, is right here, right? And there's that second oxygen. Now, when we count this and we're doing a double check, it's 1, 2, 3, 4, 5 carbons here, and 1, 2, 3, 4, 5 carbons here. That means when you do a double check over here, there should be 1, 2, 3, 4, 5 carbons. Whenever you're doing an aldol addition, you're always just going to double your amount of carbons. So when I'm looking at a retrosynthetic analysis or doing a synthesis, that's one of the things I'm always checking. I'm always counting my carbons. I'm always making sure that it's doubled. And so if we were going to write this in the forward direction, right, that is what we would get. Ooh, let's draw a better bond, right? So that's what we would get. So always, just as a nice double check, always be counting and making sure through your aldol additions that we're just doubling. Now, when we look at this, right, you can then take this and you can heat it. And if the action is heated, a dehydration occurs. And so an example of this is shown here in equation 1936. This is taking place under basic conditions, and it's going to produce both the E and Z isomer here of 2-methyl-pent-2-enol. This overall reaction, the whole thing, when we have a addition, aldol addition, followed by a dehydration, which is what we're seeing here, that's the heating, right? This first step helps us with the addition, then we're going to heat it, and now the second part is the dehydration. This whole thing is called an aldol condensation. Now, I want you to remember a condensation reaction is one where we've got these two larger molecules that come together and make a bond and eliminate a smaller molecule. And in this case, the smaller molecule here is water. What helps me remember this is like when you think about condensation on your bottle, right? There's water on your bottle, right? And here we're producing water, okay? So there's a newly formed carbon-carbon double bond, and that carbon-carbon double bond appears between the alpha and the beta carbon. So this product a lot of times is called an alpha-beta unsaturated aldehyde. So remember, unsaturated just means that we're not saturated with hydrogens. And so that's another synonym for, hey, we're going to have a double bond or a triple bond running around. And in this case, it's a double bond. The product of an aldol condensation right here can then be used for a lot of different reactions where we've got the functional groups there. Now, so this, when we look at this, right, this is under basic conditions. And because it's under basic conditions, we're going to look at the mechanism for this. Another thing that can reference this is called an E1CB elimination reaction. And this E1CB elimination stands for elimination unimolecular conjugate base. All right, sorry if that broke up a little bit there. I had to check on a furry friend in my house that was not getting along with another furry friend in my house. Okay, so back to this. This is called an E1CB mechanism. It stands for elimination unimolecular conjugate base, and we are going to look at this mechanism. So we are going to start off by drawing the aldol here. All right, and so here's an aldol. We see the alcohol group and the aldehyde functional group. Now, I'm also going to draw in some hydrogens. And some important things to know about this hydrogen is that they are acidic hydrogens. They're also the alpha hydrogens, but they're acidic hydrogens. So acids and bases react with each other. So that means when we add the base, what's going to happen is these electrons are going to come in and steal that proton. Then these electrons are going to go back up and live on that carbon. So this is a proton transfer reaction. Okay. Then what we're going to see, right, is the production of this guy. Now, this is particularly stable because it's resonance stabilized, okay? So this is resonance stabilized, and you can draw the other resonance structure, and so that's really great practice. Draw that other resonance structure. Then what we see here, right, in the next step is going to be a heterolysis. So we've produced the water, right? And we are going to have heterolysis where these electrons, right, go here to form a double bond and it bumps off this OH molecule, right? And so through this, then what we get right, is conjugated double bonds. And I want to remind you, conjugated double bonds are double bonds where it's like double bond, single bond, double bond. Okay? And so there's a few things I want to say about this. First is this E1CB mechanism might seem to contradict the general rule that we talked about for elimination reactions way back in chapter 9, which states that OH minus leaving group is generally unsuitable for an E1 or E2 reaction. But an E1CB mechanism isn't really strictly an E1 or E2 mechanism, so that general rule isn't broken. And the poor leaving group ability of that OH minus is partially compensated for by the stability that happens because there's conjugation between the carbon-carbon double bond and the carbon-carbon double bonded to the oxygen, right, in the overall product. And so we end up with some stability there. Now, dehydration of an aldol can also take place under acidic conditions. So this was basic conditions. So let's look at acidic conditions. And when that happens, again, we produce an alpha-beta unsaturated aldehyde. So you can see an example of that here. Now, unlike that E1CB mechanism, dehydration under acidic conditions does proceed by an E1 mechanism, just like we learned in chapter 9. And so notice that depending on whether, right, the alpha or the gamma proton is eliminated, the dehydration could produce either this alpha-beta unsaturated aldehyde or the beta-gamma unsaturated aldehyde. However, I want you to notice here in this alpha-beta unsaturated, we ended up with a conjugate double bond system. And here in the alpha-gamma unsaturated aldehyde, these guys are isolated, and so those are not as stable. Remember, conjugated double bonds increase the stability. And so we don't end up with any of this beta-gamma unsaturated aldehyde because this is so much more stable. So we're only going to see a removal in this E2 reaction of the alpha proton there. And of course, you could go through and do that mechanism. Now, maybe the question is, hey, Dr. Pierce, we've been talking about aldehydes this whole time. Can ketones undergo this? And the answer to that is yes. Ketones with alpha hydrogens can participate in aldol additions in the exact same way that aldehydes do. And so we can see an example of this with propanone, which is also known as acetone. I want you to notice, though, that the aldol product forms only 1% yield at equilibrium. This is generally unfavorable, in part because the product has pretty considerable steric strain surrounding this carbon. And then the other thing that we see here is that the electron donating effects from a ketone's alkyl group diminish the concentration of positive charge, right, on the carbonyl carbon. Right, and that makes it much less susceptible to nucleophilic attack. Oh, I gotta think about how to spell susceptible. Okay, there we go. To nucleophilic attack. Right? And so, because these aldol additions involving ketones generally favor reactants, chemists can manipulate the equilibrium using Le Chatelier's principle to get kind of this really nice yield. Although we're not exactly going to discuss all the specific details here, one of the ways to do this is to remove the aldol product as it's formed, right? And so we're gonna remove the aldol product as formed, and so then we can carry out the condensation reaction just over and over and over again. Sometimes this is done with distillation, which is kind of interesting, where as the product is formed, it's distilled off. So that's one of the things that you can think about. One of the things that's interesting here is this 4-hydroxy-4-methyl pentane 2-one is also called diacetone alcohol, and it's a component of printing inks. So they're gravure printing inks. I don't know if I'm saying that correctly. But basically, when in this type of printing, the image is engraved onto a cylinder of a rotary press, and then the cylinder draws up the ink and transfers it to the substrate. And the ink, to be able to do that, needs to be able to flow easily and dry quickly. And so that's one of the things this compound helps it do. So let's look at the mechanism for this. So let's start by drawing our products. Right? And so in the first step here with the ketone, still we're going to see that it's a proton transfer. And so I drew my arrow real wickedy wild. I don't want to do that. So let's go. The proton goes here, and then those electrons go right on to that carbon. So we've got a negative charge there. Now, again, this is resonance stabilized. You can draw the resonance structure if you want. That's really good practice. We also end up with water here. Now, in the next step, it's going to react again, just like that aldol condensation. What we're going to see here is it's going to react with another molecule that's floating around in the reaction flask in a nucleophilic addition reaction. And so what happens then is these electrons come here and they attack right there, and then those electrons go up on the oxygen. Now, when that happens, we end up with a deprotonated alcohol there, and so it's going to go through a proton transfer to be protonated. It'll react with water, where these electrons come in and they steal that proton and drag it back, and those electrons go up there to the oxygen. So a happy little proton transfer. And there we are. Right? So I want you to notice this is identical to this mechanism is identical for the one reaction that's involving the aldehydes that's previously shown. But again, you should be able to count and double check that your carbons are doubling. So let's do that double check really quick. 1, 2, 3. And so 1, 2, 3, 4, 5, 6. The other thing I want you to notice is if you were asked to synthesize this using a aldol reaction, you would again cut this product kind of right here to be able to synthesize it. So as you're doing these practice problems and you're thinking in the forward direction, don't forget that you also need to think in the reverse direction as well.